everyone, welcome to gemchem. Now today's video is on periodic properties part 7 video, and here we will learn about electronegativity, scales of electronegativity. And before starting, if you have not watched periodic properties part 6 video, you can watch it. I will give the link in the description box as well as the I button present above this video, that is at this position. Now let us start today's video. Now what is electronegativity? It is the tendency of an atom in a covalently bonded compound to draw sigma electron density in a covalent bond towards itself. That is, if suppose this is a molecule A and B comprising of A and B atom, then the electron density, sigma electron density specifically is being attracted towards the A, because the electronegativity of A, which is represented by chi A, is greater than the electronegativity of B. And in 1931, Pauling defined the electronegativity of an atom as the tendency of the atom to attract electrons to itself when combined in a compound. Now this one, generally small atoms attracts electrons more strongly than large ones, and hence small atoms are more electronegative. Atoms with nearly filled shell of electrons tends to have high electronegativities than those with sparsely occupied ones, because as it will gain electrons, it will become fulfilled and become stable, so they are more electronegative. Now it is very difficult to measure this electronegativity for a particular atom, and that's why to describe the electronegativity, comparison is always better than describing the modulus value. Okay, and there are different approaches to measure this electronegativity. It is unlikely that the electronegativity of an atom remains constant regardless of its environment. That is, electronegativity changes according to the environment present around it, though it is invariably assumed that it is constant. Now the electronegativity scales. Now the electronegativity scales includes Pauling's electronegativity, Mulliken electronegativity, ALLRED, Rochow electronegativity. Now this is the first one which was discovered. This is more preferred, and this gives the absolute electronegativity. Now we will start with Pauling's electronegativity scale. Now first, what it states, Pauling observed that for the reactions of type AA plus BB to give 2AB, delta H is negative. Now delta H negative means that the reaction is favored, and it is possible only if the bond energy AB is greater than the average of AA and BB. Okay, so this is the resultant. Energy of AB is much greater than the average energy of AA and BB. Next point is, Pauling also proposed that if AB bond, that is the bond between these new formed compound, is 100% covalent, then the corresponding bond energy should be equal to geometric mean of covalent bond energies of AA and BB. That is, energy of this 100% covalent compound is equal to root over EAA into EBB. It can also be represented as equal to root over EAA into EBB. Okay. Now the next part tells that since the AB bond is never 100% covalent, its structure may be written on base of ion covalent resonance. That is, AB can be written as A plus B minus or A minus B plus. See how to get the Pauling's electronegativity. First we will consider, let us write delta AB equal to EAB minus EAB, which is of 100% covalency. Okay. Now what is delta AB? Delta AB actually represents the extra stability of bond AB with respect to that of the 100% covalent AB due to bond polarity. So we can write it as extra stability, right? Extra stability of bond AB with respect to 100% covalent AB, and it can be also represented as ion covalent resonance energy, that is ion covalent resonance energy. Right. Now, the extra stability of AB bond arises due to the bond polarity, and this in turn is related to the difference in electronegativity of the constituent atoms. This idea actually Pauling further proposed that the difference in electronegativity must be related to delta AB, and he proposed this relation, that is chi A minus chi B absolute value equals to K root over delta AB, and the value of K is 0.208 if this delta is taken in kilocalorie per mole, right? And this value of K is equal to 0.1018 if value of delta is taken in kilojoule per mole, and the last factor is this value of K is taken as 1 if it is calculated in electron volt. Okay, and finally it can be written as delta AB equals EAB minus root over, we know for the 100% covalent the formula, so this one, and the final expression comes to be as chi A minus chi B equals to K, then EAB minus root over EAB whole in bracket to the power half. So from the above expression, and assuming arbitrarily that electronegativity, suppose for fluorine, if we consider electronegativity of fluorine is equal to 4.0, Pauling was able to determine the electronegativity of large number of elements from their bond energy data. So this is the Pauling's electronegativity scales formula to be applied during getting the electronegativity of other atoms. Now Mulliken scale is based on a certain consideration. Now what are the considerations? See, suppose this is a gaseous ion, E plus an electron gives E gaseous, and the delta H1 for it is minus I1. What is minus I1? We know that it is ionization energy, right? Negative of ionization energy is this one. So it is taking up electrons. So it is opposite of ionization energy, right? Similarly, Eg plus electron, then this is electron affinity, that is taking up an electron. So delta H2 is equal to minus E1. This is also in electron volt. Now if we do the sum of this, we get E plus G plus 2 electron gives E minus G, because this and this cancels out, right? Now then delta H3 comes to be as minus I1 plus IE1, right, minus I1 plus E1. The more exothermic this third reaction, okay, the greater is the attraction of E plus for a pair of electrons. From above result, Mulliken proposed that the absolute electronegativity of an element E is given by this, that is this formula. Chi E is equal to I1 plus E1 by 2 in electron volt. Okay, and this was the formula for Mulliken scale. Now in this scale, electronegativity is related to two fundamental properties, that is ionization energy and electron affinity. Thus it is more fundamental scale of electronegativity as compared to Pauling scale, and this method has simple theoretical basis and also advantage that different values can be obtained for different oxidation states of elements. Limitation is that few electron affinities are known, and it is more usual to use the approach based on bond energies. Okay, now this is important. Now we will go for the relation between the Pauling and the Mulliken scale of electronegativity. So we will see it. Basically, based upon the data on a large number of elements, the following linear relationship between the Pauling and Mulliken scale has been proposed by Bratsch, B-R-A-T-S-A-C-H, okay, in 1988, and the relation is that chi p, that is for Pauling scale, is nearly equal to 1.35 root over chi m, that is for Mulliken scale, minus 1.37. Okay. Now we will see for the next one, that is ALLRED Rochow scale. Now first in this scale, this is the 2 nucleus, that is this positive parts are the 2 nucleus and electron is revolving, and this is a covalent bond formation. Here is the electron, right, and the charge of the nucleus is Z star E. In this scale, it is assumed that the electronegativity is related to the nuclear attraction for bonded electrons, and it is also assumed that bonded electrons lie halfway between the covalent distance, that is distance between two nuclei. Thus the distance of bonded electron from the nucleus corresponds to the covalent radius. Okay, now see, basically in 1958 ALLRED Rochow considered that electronegativity in a different way and worked out the values for 69 elements. They defined electronegativity as the attractive force between a nucleus and an electron at a distance equal to the covalent radius, and this force was given by this formula, that is F equals to E square Z effective, or we can write it as Z star, this is optional, divided by R square, and proposal was chi is a function of Z star E square by R square. Okay. Now we see here a graph. Okay. Now what is this graph? This is a plot, that is Pauling's electronegativity plot, that is this represents the Pauling's electronegativity, and here Z star by R square covalent is being done. Now the Pauling's electronegativity for different elements were then plotted with respect to Z star by R square covalent, where R covalent is in angstrom. Okay, the best fit plot was found to be a straight line and its slope was 0.359 and the intercept at y-axis was found to be as 0.744. By applying this y equals to mx plus c, the electronegativity of ALLRED Rochow was found to be 0.359 Z star by R square cov, that is covalent radius, plus 0.744. So this was the electronegativity obtained for this scale, and this electronegativity is represented as absolute electronegativity. It can be also manifested as follows. This formula can be also obtained from another method, that is the latter case. The nuclear charge was modified by the screening factors for the orbital electrons. The screening factors vary depending on the principal quantum number and the type of electron, that is S, P, D, F. The screening factors have been worked out by SLATER. So this provides a convenient method of calculating electronegativity values on the Pauling scale of values. These F values, that is the screening constant values, may be converted to electronegativity scale on the Pauling scale of values using this empirical relation which we have seen now. The electronegativity so obtained agree quite closely with those obtained by Pauling and Mulliken. As oxidation number of an atom increases, the attraction for the electron increases, so the electronegativity should also increase. Okay. Now we will see for the next part. This method depends on measuring of covalent radii. Now covalent radii, and these are obtained with greater accuracy by X-ray crystallography. So it might be expected to yield very accurate result. This is not so because although the interatomic distances can be measured very precisely, covalent radii are much less well known because of multiplicity of the bond is not known for certain. That is, the bond may possess some double bond character. So there is something difficulty present in this method also. Now this is a workout. Okay, the FF distance of fluorine molecule or fluorine compound is 141.3 ppm, that is picometer. Calculate the ALLRED Rochow electronegativity of F2 using Slater's rule. Now first, as fluorine is being given, so we will use Slater's rule using, let me take another color, Slater's rule for fluorine. We know the grouping, how to group it. Now if you have not seen the video on Slater's rule, please do watch it. It is already given in the channel. I will give the link in the description box as well as the I button present above this video. So this is how it is grouped. Okay. Now contribution. Let us write about the contribution. From here the contribution comes to be as 7 into 0.35. We are taking the total contribution, no electron specifically, and for this it is 2 into 0.85, and the total comes to be as 4.15. And we know for fluorine it is actually 9. So the Z star comes to be as 9 minus 4.15, which is nearly equal to 4.85. Right. Now we will use ALLRED Rochow scale, that is using AR scale of electronegativity. What we obtain? X, that is chi, actually that is chi AR equals to 0.359 Z star R square cov plus 0.744. Now see one thing, we have been given the diameter, right? Because the bond distance is the diameter, so half of the bond distance will be taken. So Z star comes to be as 4.85, and this one will be half of the diameter, that is 41.3 divided by 2 whole square plus 0.744, and this comes to be nearly equal to, on calculating, 4.23, and this is the electronegativity of F in F2, right? So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.